individual. And then this one is the only one that is integrated. Okay? So, where's William? When we need him, we sit here. Let me get my... Okay, to start with, the way of introduction. My name is Dr. Emmanuel G. Moya, and they call me Noel. 40 years ago, I went, my first station was in the US, where I learned a lot of buildings and contracting and so on. And then later on, I was sent to Canada to start this kind of technologies. So most of the technologies that you will see were discovered, produced, developed about 40 years ago. And about 25 patents was written through a company that I work with. Two companies that I work with, majoring in filtration. One is Claude Laval, based in Fresno, California, where I developed the centrifugal separator filtration system and also a multimedia filtration systems. If you Google my name, Emmanuel G. Moya, you will see the technologies I developed over years. And then I moved to Griswold temperature controls for cooling towers. So all these systems, every time I discovered some problems and I solved it, I filed for patents. Okay, but those years, because you work with a company, you don't own the patent. You author the patent, but you don't own it. For $1, they bought your idea. So I wasn't able to commercialize based on the idea. So I waited until 20 years passed, the patent is gone. I reintroduced the technology with some modifications. So the things that you will see here is the latest innovation on these technologies. Remember, we're dealing with a non-chemical water treatment system. It's a big challenge. How are you going to kill bacteria? How are you going to remove the toxicity in water? Okay, like chemicals and so on. How are you going to remove the scales? So in this introduction, you will see the methods that we employed, having no bacteria, no scales, no deposit, and so on. So 3 years ago, the patent was released. I was able to modify it a little bit to conform with Canadian standards. So I came back here and introduced the technology. But before I did introduce, there's about 2 or 3 installations that I started with in the US. It's not a major installation, but these are high-rise building, hospitals, and smaller condominium, so on. But it was proven the technology works. So I made them my guinea pigs. They bought the system. They paid for it. As soon as I know that this is successful, I started bringing it to Canada. And during the time that I am introducing the system, or I was introducing the system, everything was made in Canada. We have a shop in Brantford that started everything, from here to the US. And I never did make it in the US. Only the things that I buy came from the US, but everything that I manufactured came from here. So knowing that it's a Canadian technology, they now discovered that I have a shop in Brantford that I produce all these products. I said, well, this is Canadian made. And, you have to put North American made. So nobody will question you. So in all the products that I have, you will see American plug and Canadian plug, just to be safe and neutral. And so nowadays, there's nothing neutral nowadays. You have to be either Canadian or American. Okay, so rest assured that this will be made in Canada. Okay. So William is our vice president in marketing and sales. He started introducing this product about 4 months ago with all the patients, because I told him, it's not negative, but I warned him to introduce this product, you will have a hard time because you are actually going against the chemical people. Chemical people are very high and very big. It did happen to me in the US. Every time that I have installation, they pull the plug. Knowing that I'm using electricity, they pull the plug. So when you don't have power, the unit will not work. So what I did, I put a camera and I put a system that will detect the removal of the gadget. Every time the power is off, my cell phone rings. Okay, your power is off on this station. So I know. And then with the camera, I could detect who did it. Okay, and I'm sure in Canada it will be the same because the chemical people are very big and very vigorous in doing all these negative things. At any rate, here's the product. We call it a HVACR, which is heating, ventilation, air conditioning, and refrigeration. And it only involves, right now, the cooling tower and condensers. Okay, if you have cooling towers, there's a good chance that you're using a lot of chemicals. And condensers as well, you're using a lot of chemicals. So what we did, we counter the chemical by knowing how much chemical you did or you are using. And instead of selling the capital expense, because it's very hard to sell this as capital expense, you need a lot of approvals from the board, from the bosses and so on. So what we did as a matter of introduction, we introduced the system on a chemical basis. That means if you're paying, say, $100 on chemical every month, we'll come in, counter the same $100 installment until you pay the whole system. So remember, the system has an ROI, 3.2 years the most, and less than 3 years if you're using a lot of chemicals and water. And let's say you're paying that chemical forever. With this system, you have an ROI. At the end of 3 years, you don't have to pay unless you're leasing. But we normally, tell you, okay, you can get this based on your operational expense, your OPEX. So that means if you're paying $600 on the chemicals, we come in at $600. So you don't have to alter anything that you are in the budget. So with $600, let's say the amount is $6,000. So in so many months, you're paid with this equipment. And you don't have to worry about paying anymore. All you need is maintain the equipment. Okay. So the system is integrated into one. You have water filtration, you have descaling, and you have disinfection, and you have water conservation. Later on, I will explain little by little, but we will do a slide by slide. Okay. Next slide. Okay, there are 3 objectives that we have. The primary is to find an acceptable solution to replace hazardous chemical used in HVACR, cooling water systems, with emphasis on the environment and human health, control and eradication of Legionnaires' disease. This is number 1. Secondary is to provide substantial savings in water, power, and labor. And tertiary is prolong the life of the equipment. So one by one, I'm going to explain. The number 1 factor is actually with regards to chemical, because once you handle chemical, there's a lot of toxicity, hazardous and so on, like handling bromine, chlorine, and anti-scalant. There's a lot of toxicity on it. And when you add this for cooling towers, you're adding pollutants in the environment. So this is one of our objectives, to remove all these pollutants. Secondary, or within that context, is the eradication of Legionnaires' disease. You know what happened when you have a Legionnaires bacteria? This happens from dead animals. And this could be dead birds, dead rats in the cooling tower basin. So how come you have dead birds? In wintertime, or not even wintertime, in the cold season, birds, especially those who are going to give birth, they have to find a warm place so they can give birth, lay eggs and so on. And they found the best place for that is the cooling tower, because the temperature exchange is conducive, the warm temperature. And so with rats. In New York, it's number 1. Rats will go inside the tower. Since they don't know how to swim, once they fall, they die on that one. So that's the start of bacteria. With the bird, the moment the propeller, the fan actually starts, they get excited, they want to go out. And they cannot go out, so they clip their wings, they fall. Once they fall, they die. So it's start of bacteria. Anything, even in bigger or smaller insects, the accumulation of insects inside the water gives you bacteria. Algae formation also will give you the same bacteria and so on. So when this is misted or vaporized in the air, You have a lot of droplets, and when that droplet is ingested by individual, especially with those with lung problems, that is the start. And you're given within 10 to 12 days. If it's not controlled, there's a chance that you will die. In New York, about 6 months ago, there was 22 deaths. 1 year ago, there's 34 deaths. 3 years ago, there's about 60 deaths on Legionnaire's disease. And you know why they call it Legionnaire's disease? In 1976, there is a convention in Pennsylvania. And all this convention was attended by legionnaires. Those legionnaires of America, those are the veterans. So the building was so sick that there was no good ventilation, and they ingested this bacteria from the cooling tower. So little by little, a lot of people died based on that. So science proved that it is bacteria that killed these people. That's why they call it Legionnaire's disease. For no other reason, just Legionnaire's disease. So from then on, it is called Legionnaire's disease. So the research that I did 40 years ago, I started the research. They look on the paper that I wrote, and they came back to me, what is your solution? That's the reason why I came with this technology. So integrated technology, I put all the patents that I had in the past 40 years, put it together and came up with this integrated solution. And now they are using it. So the savings is substantial because the treated water, the filtered treated water, will return to the system. Instead of dumping by bleed off or blow down, it will go back through the filters, and then the solids, the sediments, even the bacteria collected by the filters, the filter banks, the treated water will pass through the filter and return to the system. So that is a major saving, between 60 to 70% water saving. 95% is chemical, between 90 to 95 because you are not using chemical. You don't use bromine, you don't use chlorine. You use the same water that you treated. So there you go. Only 5% because you need to clean it every year. So 5% is used for cleaning the system every year. Now, prolonging the life. This is one of the best issues. I remember years ago, one of the charts here required to replace the boiler. The boiler is too old, more than 25 years old, and the priest who managed the chart said, I need to replace the boiler. So I told him, if you give me a chance, I will prove to you that this technology will extend the life of the boiler. He said, well, I've been using $600 on chemical just to maintain the boiler. I said, let's try. So he gave me a try. For X amount of money, he gave me a try. After 2 weeks of using the system, all the old scale came out from the boiler without using chemical, without punching the tubes, without opening the boiler. Everything came out, and it was shown in the presentation. So every day for the last 3 months of that, they collect a lot of scales. And after that, they stop because there is no more scale. And when we open, I said, we have to open. You have to give me a chance to open. When we open, the tubes are very shiny. And we took a small sample of the coatings that envelope the tubes. The lab said it's an aragonite coating. Aragonite coating actually came from calcite. So I'll explain that again on some of the slides. Okay, so it protected and it's prolonging the life of corroded equipment. So instead of buying a new boiler, he just used my system. Until now, they're using the system. They save $600 a month on chemical. Remember, winter time, you need a lot of boiler. And from then on, they said, Noel, I will try to help you. I said, not yet. I'm not prepared because I don't have the resources to do it. But literally, we have the science. Okay, the next slide will tell you how smart you are. Okay, next one. Do it on the slideshow. Yeah. There you go. Slideshow. There. Okay, the observation that we had before we wrote the patent are the problems with traditional chemical systems. Okay. Oh, what happened? Next. Just click it and it will give you the next. Okay. The number one problem with chemicals is the hazardous environment on it. Remember, when you're dealing with chemicals, sometimes you need to have a certification or you must be certified chemist to deal with it. It actually affects your lungs. Number one attack is the lungs and the eyes. Next. It's unreliable. Sometimes if your dosing machine or the pump that doses the chemicals malfunction, there's a good chance that you don't have an injected chemical and you rely on that. If it's unreliable, you cannot use it. Okay, next. Difficult to maintain critical levels. You need an actual presence of operator to look on the critical level of the chemical on a daily basis. This is one thing. If the guy is absent for 1 or 2 days because of sickness, you will have a problem because the critical level is not maintained. Sometimes they use a sensing device to maintain the low and high level of that, but chemical is, it will attack whatever properties of sensor you have. So it becomes unreliable, difficult to maintain, must be handled properly. Okay, since this is hazardous, there's some signs that you have to be aware of that you cannot even go near, acids, muriatic acids, things like that. It requires a spatial handling. Next one, difficult to handle. As I've said, you require a lot of certifications and then compliance as well. All the chemicals that are using for water must be compliant with the standard. Okay, you cannot just use or overdose chlorine because you have a lot of bacteria. You must have a compliance on how much dosage you need to comply with the standards. And it requires maintenance. Daily maintenance is much needed on this. Levels, the amount of dosage and so on. Messy and unsightly. When you look on chemical, bulk chemicals, drums and so on, the smell alone, you will say, oh, it's going to be messy and so on. You don't want to handle it. You don't even want to touch it. Human error, you're prone to human error. We're just human beings. So from time to time, we neglect to maintain, the cleanest point. Okay. So here's the real problem. Real problem actually translates to the disease transmission, and number one is Legionnaires' disease. Sometimes Giardia, sometimes E. coli, Listeria, and so on. So this is especially in hot tubs, cooling towers, hot water tanks, large plumbing system, decorative fountains. Now, why temperature? Any kind of bacteria really survive and thrive at 100 to 140 degrees Fahrenheit. So if you're using this on hot tubs, saunas, and so on, at 110 to 140, your bacteria is thriving. If you increase your temperature to 140, 150, there's a good chance that you're using a lot of power. That's why they stop at 120 on putting this in your hot water supply. Okay. Okay, now if you look, can you go back? Go back, okay. This picture is actual microscopic shot of the Legionnaires' disease. That's how it looks like. So if you see this in one of your lab, there's a good chance that you have a Legionnaires' disease. That's the only picture of Legionnaires' disease available. You cannot get any other picture. Next one. So according, best practices for control of Legionnaires, actually we are member of the Cooling Tower Institute, and we got access through the ASTRE membership. ASTRE is the Association, American Society of Heating, Refrigeration, and Air Conditioning Engineers in the US. And it's also present in Canada. ASTRE is North American. Okay? So we follow that standard. Okay, next one. Okay. We use ultraviolet in our system as well, if it's needed, because we have to analyze what kind of water you have. So if we need,
Take a call, and I missed part of the Legionella stuff.
Yeah.
So you're
Yeah.
treating the water that's coming through there without chemicals.
Yep.
You're treating it with UV.
UV, ultraviolet, but it depends on what kind of bacteria that we detect in your system.
Right.
If it's really very toxic or very dangerous bacteria,
High levels. Or
high
whatever,
level,
yeah.
we have to use the ozone.
Ozone or UV.
or UV, or a mixture
or
of
a combination of
UV,
the
combination UV, ozone, or copper silver.
Copper silver?
Yeah.
Okay.
It's one of the best because during the time of Romans, they use copper. Okay.
Yeah.
And sometimes you see them with silver on their hand.
Yeah.
So when we analyze why copper and why silver, copper actually controls growth of bacteria. Silver kills bacteria. So when we combine that during ionization, we are assured, especially in a swimming pool,
Do you put probes, copper silver
Yeah.
probes in the water system?
in the water system. Actually, it's not in the water system. It's in a small tube. We put copper and then silver, and then we have an ionizing effect like electrolysis. And that will give you an ion depending on amount of bacteria you have.
You run a charge between the two.
Yep, you have the charge.
Okay, perfect,
Okay,
okay.
different charge. Okay, next. Ozone electromagnetic. So here's one sample of ozone. I don't want to turn it on because it's very potent. You can smell it, and literally you will have problems with your throat. So how we discovered ozone? Ozone is a product, the third element of oxygen. Okay, so when you have air like this, you concentrate air, you produce 30% oxygen on that room. Okay, so with 30% oxygen, you pass the oxygen molecule, the O2, to a coronal discharge, a plate that is electrified. So when that ozone passes through that plate, it is burnt. So the burnt ozone becomes your O3, your ozone. Okay, O3 is your disinfectant, your oxidizing element. So when you oxidize an element, it becomes crystal, it becomes powder. Okay, more that it becomes nucleated with a combined electroprecipitation, which is an electronic frequency. Okay, so that's how we got ozone from the start. Oxygen burned becomes ozone, and we use that, we inject. And we have a rule of thumb: for every 100 GPM, you need 1 gram per hour. So we made our module in 100s of gallons per minute. So if you have, say, 500 gallons a minute, you need 5 grams per hour. And we tested that, and it's very efficient. The efficacy of that combination of calculation is very efficient. So you don't actually overdose your ozone, because the moment you overdose, there is a tendency that you will have a headache. Okay. Scale control. This is what you call descaling. By introducing frequencies, you actually introduce a descaling method. That means you reverse polarity of the ions. And how one of the academic in one of the university challenged the way we produce the frequency for descaling. Okay, so I told him, get me a glass of clean water, the one that you drink, and get me a glass, the same volume, of hard water from your cooling system. So 2 glasses. I have a tuning fork and I have a spectrometer. Okay, so the clean glass, I hit my tuning fork, and within one inch, there's a tuning fork, and it produces a frequency. With the spectrometer, we measure the frequency. The clean water is less than 5 kilohertz on the frequency. The bad water, I hit it the same method. I took the frequency, it's about 25 kilohertz. So the difference is 20 kilohertz. So the amplifier that we made, this is good for the house. The amplifier that we made produces 20 kilohertz. So a width band between 5 to 25 kilohertz is sufficient to remove all the scales coming through the house. Your heater, your boiler, anything that has water, hot water, if you pass it here, the scale is removed or prevented from binding to the surface. So we have an actual scale, and we have another point that is clean-up scale. And only introducing 20 kilohertz band, So here's the coil, which is a cable, a pipe wrapped to a pipe. You don't need to cut the pipe. You just wrap it according to the frequency that you want. If it's 25, you have 25 wraps, okay? and we measure the frequency based on that with our oscilloscope, it produced 20 kilohertz. That's enough for the house. Okay, for the big condensers, big pipes, depending on the size of the pipes, we wrap it the way it should be on the frequency. So that is the way we depended the thesis, you know. So they require a thesis, they require a proof. So we have a proof of concept, and when we put it together, we produce the same frequency as what is registered. And that's why they got our patent. The patent was released. Scale control, biofilm control. This is one of the issue with cooling towers. You know, sometimes you have all the grease, all the biofilms and so on. Biofilms are so hard to detect. It's actually on top of the water, sometimes at the bottom of the water. It becomes a slime, okay? So once you touch the bottom, you feel a slimy, or once you touch the top, you feel the slimy content of the water, and that is biofilm, okay? We remove the biofilm by the ozone. It oxidizes the biofilm, okay? Bulk water is one issue because it's hard to monitor. With the system, we have a WebTroll or wall cam that we can monitor whatever water we're treating. So end of the day, it will give you a report, a monitored report saying, okay, your TDS so much, your conductivity so much, alkalinity so much. You know, we have that ability. That means all you need is open your cell phone and read on the data that is published based on the protocol. So you will see every day, what is my TDS today? And it gives you a warning, you know, it gives you a blink. Once your TDS is very high, it blinks. Something's wrong with your system. So you call your operator, check this and check that, and so on. Okay. Stagnant water elimination. Where is stagnant water in the cooling tower? We call it the dead leg. This is the leg at the bottom of the tower that is considered dead, but this is the habitation of bacteria. Okay? Once bacteria is in that, you know, you call it the stabilizing leg and so on. So it is in between all these towers. They have a neutral leg on that one. So it stabilizes pressure and flow and even level. But that is stagnant. It doesn't flow. So what we did, we oscillate it with the frequency resonator, that one, and then we have the injected ozone that goes through it. Okay? So with that two elements, ozone and precipitation, kills the bacteria and prevents growth of scale. Drip elimination lowers drip rates and so on. It is actually on the evaporation rate. It's calculating the evaporation rate. But because the system actually reverts back the water, we lessen the drift by doing that. We force it to go around. Okay? So the drift is lessened, not really reduced, but just lessen a little bit. Customized mechanical design. So depending on the space that you have, sometimes you don't have the space, we'll customize the design to integrate with your system, with your rooms, what is available in space. That's why we call it custom built, you know. Sometimes your head space below the cooling tower is very low. We can make the separator inclined. So here's your separator, and this is the internal, okay? So water will go through the tangential inlet right here. So when water goes in, it's spiral, centrifugal motion. So when it's spiral, all the solids will drop at the bottom. So you have a solenoid actuated valve that purges it. You know, when it purges, it goes to a filter back housing, collecting the solids, and the filtered water will return to the system. Okay, now the vortex is created in the middle by Venturi. So the vortex becomes a clean vortex, and that water goes back to your system. So it's repeated so many times, never ends. Even if you're operating 24/7, which we are in the US, we operate 24/7, and when there is trouble, I'll open my cell phone, and there you go. You have a problem. So this is the internal of the separator. I invented this 23 years ago, and it's being used by all companies all over the world. And the number one company who bought the idea is Halliburton Schlumberger, because they are pumping oil down about 2,000, 3,000 feet below. So when oil on a freshly drilled well, when you have crushed stone underneath and you pump it on your turbine, within 2 days, your shaft and your impeller is gone because of the abrasion. So they approached me, can you prevent solids from attacking my pump? Because the pump is $250,000 and it takes them 2 weeks to remove and replace. So the losses are enormous. So I said, how about this idea? Before you pump the liquid, I'll remove the solids. That's why I created a tangential inlet. So when solids or when liquid enters the tangential inlet, it will swirl immediately. So when it swirls, it creates centrifugal motion. Solid goes back down, and then the liquid, the good liquid, is returned. So you have less abrasion on your pump. So they bought the idea. Imagine a small company was able to make millions out of this design. But I'm just an employee of that company. I created the technology, you know, but I didn't make money out of it.
So the material that you're pulling out of that
Yeah.
centrifugal,
This is mostly our carbon steel.
right?
Yeah.
But are you having to change?
Nothing.
No, like the filter. Are you having to change?
No, because down at the bottom right here,
Yeah.
you have a solenoid actuated valve at the bottom, and it's vacuum. It's connected to a vacuum on the ground.
Oh, so it just takes it away.
Yeah, takes it away to a
Is
truck
there
or
any
whatever.
erosion or any kind of
None.
damage done to your
None.
impeller?
You know, the filters that I connected there about 30 years now, it's still there.
Okay.
It's still there. But the gauge that I use is all Schedule 80, very thick.
Yeah.
So when we pulled out one and we cut open, everything is shiny. Everything's shiny. So I said, well, I don't have any business with you. You know, I cannot even sell you the internal. No, everything is good.
No, that's excellent.
Yeah. So that's how it looks inside. Just to show, I have a unit that is really operating by. I lost the bag. Somebody took it. But that's how I created it. You know, with a small spiral design on the inlet, right there, and then the vortex with angled traps, and then there's a gap between the pipe
Yep.
and the spin plate,
Yep.
and everything goes down, so they cannot go up.
But what happens if your particulates are a little bigger than that gap?
Well, it will maintain here,
Oh,
and then
stay
it
there.
will maintain here. It will stay there until it move until it goes down. But
So it even though the particulate's big,
Big.
it kind of like all the other stuff hitting it.
yep, it
make it
will.
smaller
It will
and
be
it'll
pushed
eventually
down.
come
It becomes smaller.
I see.
Besides, before we design this, we take samples of their sediments. So the bigger the sediments, the bigger the gap. Okay, so it depends on your sample.
Okay, I see.
And anything that is
That's why it's custom.
exactly anything that's standard, like outside, we have a hole here, a manhole. We call it just hole because you know, sometimes the ladies are sensitive.
Yeah.
You always call that manhole. How about us? You know, okay, there's a hole. There's a hole. So when you have a hole, you can open it and take a look.
Okay.
You know, so that's a very simple design, but it's been there for quite some time. 40 years now. Okay, so side stream filtration. Here's the thing. If you have a big cooling tower or cooling system, like you're doing, say, 1,500 tons of refrigeration, this is actually gallons per minute. Okay? So the rule of thumb is you multiply that 3 times to get your total recirculation flow rate in the system. So 1,500 tons of refrigeration is actually 4,500 gallons per minute. Okay? The side stream works with starting with 5, 10, 15, 20%, which is more economical. Because if you try to filter the full amount, 4,500, it's going to be a huge filtration system. You don't need that because with 10%, you are assured of 4 times return per hour. So 4 times the same water will return to its location. So with that, we heat the water 4 times per hour using a very small design. So very small footprint. Okay, next. Oh, this is where the copper-silver ionization is, you know. So you have a copper that prevents bacteria from growing, and you have silver that kills bacteria. So we ionize both copper and silver rod by introducing a small voltage on it. So the ions of copper and silver is released through the water. When it's released, it will find the bacteria. It will attach to the bacteria, and then by electroporation, when you electroporate a bacteria, you actually penetrate the skin or the membrane of the bacteria. So when you prick it, the bacteria becomes wounded and they cannot survive. They die. And that is the work of copper-silver ionization. So introduce copper and silver, because of that ions, it actually kills bacteria by electroporation. Okay? You're heating the bacteria from the membrane to the inside. So they die. Okay, this is now a system that requires a multimedia. Why multimedia? Multimedia can go down to 1 micron. Okay? Bacteria is actually 1 to 2 microns. So if you want to use or to remove a lot of bacteria, you have to use a filtration system, like a multimedia. So the same scenario, the same system that we have. So this is the basin of the cooling tower. So that basin actually collects all the water from the condenser to the plastic film, and then it drops right here on the basin. When it drops, because of the change of temperature from, say, 100 degrees on the top from the condenser, with the film, it brings it down to about 80, okay, or 90, something like that. So there's a 10-degree temperature difference. So with that water actually cooled down, but that water contains a lot of sediments. It could be the scales that we move or remove, and then everything drops on the basin. So what we did with our system, we deploy a manifolded spray nozzles. So you will see a lot of nozzles towards the suction of the pump. So we angle it in such a way that we are pushing all the sediments towards the suction of the pump, right here. So those are the suction points, and then we bring it back, right here. We bring it back to the suction of the filter, okay? After the suction...
Sorry to interrupt. I have to run.
It's okay. Thank you. I understand. Yeah. We will send you these...
So I grabbed your brochures, but
Yeah.
I think we should schedule maybe something online.
Yeah.
With Stefan's team
We will.
as well after this,
Yeah.
because it's important.
And
Yeah. Okay.
actually, William probably knows your contact, so
Yes.
we will connect.
Okay. Thank
Okay.
you. Thanks for having me, and thanks for the food.
Thank you. Thank you for attending. Yeah. So when sediments are here, so the nozzles actually pushes all the sediments towards the suction, and then the suction point, from there, suction point goes right here, manifold goes to the suction of the pump through the strainer. So majority of the big scales are actually deposited in the strainer, and then the pump transport that to the filter, and then when it goes to the filter, it actually passes a frequency, which is our precipitator for the scaling. So when the scale actually nucleates, I will show you the pictures on the microscope. When the scale actually nucleates or becomes amorphized, it becomes bigger, they blew up, and the filter will remove it, okay? When the filter backwash, all the backwash water passes through a filter bag. So the collected solids are in the filter bag, and the water that's treated returns to the system. So there is a returning point. So once that water returns, you actually save about 80% of water. So it goes back to the same thing. And then on the finality, we have an ozone. The ozone is injected before it leaves, the filter. So there is ozone in this water because we have an ozone injected right here. It goes back to the nozzles. So the ozone, the water with the ozone actually is injected back to the basin. So whatever bacteria you have in the basin is killed by the ozone. So it's perpetual. It goes back and forth, until you stop the system. Very simple, right? So you suck all the dirt, you send it to your filter, you electrified it with your frequency, and then you oxidize it with your ozone to kill bacteria. Again, it goes back and forth, Okay? Now on the next slide, I'll show you how you protect your condensers and or boilers or heat exchangers. So before, on the return or the supply, before it hits the condenser, you put another precipitation device like that, depending on the size of the pipe. So this frequency will attack the tubes to remove all the existing scales. So the oscillation of the water with our frequency will remove existing scales on that one until the scales is deposited back to the basin. Again, the basin has our nozzles, and then with our filtration system, it goes back to the supply, and then return, and then back again to the supply, and so on. But you have a filtration system that cleans everything. At the end of the day, your water is very, very clear. Or at least free of debris. Okay, next slide. Okay, this is what I'm saying, the magnified version of the calcite. The one on the left is actually the ionic states. What do you mean by ionic states? This is the agglomerated states of the scale. So the scale is just forming without our system. As soon as you put the system, it becomes a batterite calcite becomes amorphic. When you have amorphic, it blows like that. It nucleated, it blows like a popcorn. So when it goes bigger, your filter can remove it, and it becomes softer. That one is solid, very hard, and this one is soft, just like powder. So when the filter is activated, you can remove it by backwash or by removing the filter bag. Okay, next one. So this is what I'm saying, microcontrol. With that system and with the ozone, we kill the bacteria by two things. The electroporation right here. We attack the membrane by pricking it open. So when you prick it, the bacteria cannot survive. They cannot grow, they cannot, because they are wounded. And they have lost the appetite to eat and so on. So the growing mineral crystals is encapsulated microbes. So when you have a crystal, powder crystal, and you have a microbe, two ways of killing, electroporation, operation, and encapsulation. So you encapsulate the bacteria like that until they die. And then that molecule becomes bigger until your filter removes it. Okay? So that's the science of the combined system, the integrated system. The next one. So this is how it looks. So you have a section of the pipe that has the cable, and then it produces a triangular wave. It's not sinusoidal, it's not digital flat, it's not analog, but there is a combined triangular wave like this. Okay? So why triangular? Because we introduce another pulse, an extra pulse, so that the strength of that pulse, whether it's very short but very powerful, it kills the bacteria that it can see. Okay? So the bacteria becomes, eradicated because of the extra pulse that we have. So at the end, you will have a lot like this, okay? Passing through, the bacteria starts right there, bacteria, using our system, it kills the bacteria, it becomes powderous or bigger, and we collect it with our filter. Okay, next one. These are before a company in the Philippines and here in New Jersey bought a bigger system. They had to run a proof of concept, a POC. So the POC that we have is very small, like 1/10, like 10 gallons per minute. Just to prove on a small section if the system is efficient enough for what we are claiming. So they have this, the red ones, you have green ones and red ones, green ones and red ones, and so on. So the green ones are the chemical, and it has a period. It's monitored by Alpha laboratories in the US, New Jersey. And the red line is the acceptable level. You have the lowest level, you have the maximum level, but the red lines are the acceptable level. If you calculate your LSI, your Langley saturation index or scaling index, you will see that the red lines is actually within the range. So for example, recirculating water and makeup water. Recirculating water is the water that we have in our system. Condensers, cooling towers, that is what we call recirculating water. Makeup water comes from, majority are the city or well, deep well. So take a look. The pH level on the chemical side, on recirculating water, is very inconsistent. And they are on the high side on that one. The proof of concept that we had is near or always in the middle, the red dots. You will have this presentation for your reference. Okay, that is recirculating water. That means this is the water that you have on the cooling system. Makeup water from the city is still, chemical is very inconsistent. So that inconsistency costs consumers a lot, the users, it will cost you a lot. But the proof of concept stays near the standard. Okay? So you can run through it, calcium hardness, recirculating, makeup, and so on. Take a note that when you have a calcium hardness on the green, on the lowest side, you have a tendency to scale. But if you stay near the red line, you are actually preventing the scale formation. And that's proven on this. Just maintain a level that is near that, and when you open the condenser tubes, you don't see any scale. You prevent scale forming. Alkalinity is the same thing. Okay, chemical is almost inconsistent as well, but proof of concept, it's so near the red line. The same thing with recirculating. We are near. Chemical, very inconsistent. So that means if you're inconsistent, you have to have somebody every day to check on your chemical levels, your dosage, and so on. With this proof of concept, nobody was there. We just let it operating 24/7, and at the end of the week, we monitor whatever data we got. Okay, so that's how our system. Next slide. Same thing with TDS. Take a look. The recirculation, the system water, inconsistency, our POC is near or within that level. With makeup water, we're flat. That means we are doing a lot better, below 200 parts per million or even 100. Conductivity, makeup, and recirculation. Look at the conductivity. Chemical, you have a spike, okay? And then they have to come back and put the right dosage. They come up with that, but during high temperature, it spike again. But with us, the proof concept, take a look. It's even below that line. That's conductivity. Temperature remain, but here's the thing. On the next slide, if you're using condensers, take a look. There's a condenser approach right here. Without our system, the normal condenser rose up to 4 degrees. The increase in temperature in the condenser is 4 degrees. Our system maintains a less than 1 degree temperature change. So when you have a big temperature on the condenser, that means you're drawing a lot of power, a lot of electricity, okay, because of the scale that is formed. Okay, you have to do a heat transfer on that one, so you require a lot of power to maintain that level. So with us, the condenser approach, this is the decision-making item that these guys did. The condenser alone, if they're using a power like 100 kilowatt hour on that unit alone, that one is 100 kilowatt hour. This one is less than 20 kilowatt hour. So they have a data that they formalized, and they said this system proved that it is very effective. No scales. So after 6 months of trial, they opened the tubes, they opened the condensers, and this is very shiny. This one, thick scale. So this is the deciding item on that. And everything, they look on everything. The ORP is the oxidation reduction potential, which is the disinfection effect of the system. Okay, it tells you that my system, because of the high ORP, was able to kill the bacteria that we encountered. The chemical system, take a look. The most that they have is 200 millivolts, okay, or microsiemens per centimeter. Ours is in the 400. So all deciding factors, they said these are the deciding factors that we have. We don't need to go farther. So they selected us. And I said, we are still new. We are not even 3 years old. They said, we don't care because you have a proof of concept. And that tells us that your unit is better than competition. And when they place an order, it was so big, and I told them, I cannot deliver. Why? I don't have the resources to put it together. So you had to give me a down payment or deposit. So they give more than 50%. That's why we were able to deliver. This unit is for 4,500 gallons per minute. It's huge. So immediately I told them, I cannot deliver. I don't have money. Okay, since you are small and you are young, we'll give you the money. I said, I'm not young. I'm 73 years old. No, your company. But because of that experience, they said, okay, I trust that you deliver. And we're able to deliver. This one goes to the Philippines, one of the biggest data centers, just like Google. When I did Google 23 years ago, I was starting this technology. And Google in Palo Alto, the same with Facebook, they said, well, your technology is very young at that time, 23 years ago. But we recognize science. That's why we give this to your company and do it for us. Until now, 30 years almost, the unit's still working. And we don't have a business with the unit. Not even a part of the impeller or the pump is broken. We just maintain the same flow, the same pressure every day in, day out. System is still working. I said, can I sell you something? No, the system is working. There's a saying, if it's not broken, don't touch it. So I said,
it
yeah.
basically helps to extend the life of the
Yeah. But it is really, sometimes you thought that you will get more business because it's more than 20 years. No, you check on them. No, until we expand, we will call you, but we're not expanding. We're maintaining the same system. So, okay. But I use them to get into other accounts.
Well, you use them as a reference.
Yeah, especially now that I'm independent. I don't have an employer. I am doing it myself. And with these guys that I have, I'm also training guys, young guys. Whether you're Canadian, you're American, or whatever, I'm going to train you, especially if you're interested. So this is how we are. And I'm sure we can help. If you have this kind of problem in your system, we can come and help. All I need is the parameters of water that you have, the size of the system. Okay. Next one. Let's see if you have. Okay. These are the existing ones that I have. Okay. So this is the unit. You have the control panel, the separator, the ozone, and the precipitator, and the discharge filter. The size of this for a 4,500 tons of cooling is 4 feet wide by 6 feet long by 6 feet high. That is the dimension. And we can go from the incoming water from the city. I'll put a coil right there. There's a coil. And there's the unit at the end. Okay? It protects all the system or the water that goes through the building. Okay? It rearrange the water molecule, the ions, and so on. And that's the main system for the cooling tower. And this is the system for the boilers. So here's your boiler. Here's my system for that. And I put just 2 coils on the supply and return with 1 amplification. So it removes the scale. And the water's opening as well on the incoming water. So those are the cooling towers that I have. 4,500 on each building. There are 2 buildings. Okay. This is one application. Okay, next. Different applications, a smaller building, like 500 tons of cooling, separator system, and Presbyterian Hospital, I have a multimedia because they require 1 micron of filtration because of hospital, sanitation and so on, sterile. And this is a district cooling for Chesapeake in Washington, DC, right here. So here I use a copper silver because most of the bacteria is killed by iron, by copper and silver. So 100% I use copper silver on this one. Okay, next. And this is the church that I help. You know, the boiler is ready to be replaced, 20 years old plus. And this is the scale that I remove every day. Bucket of scales every day until it becomes shiny and they don't need any chemical, they don't need any cleaning and so on. So that's the evidence. They remove that. Okay.
So is the equipment only used on the condenser side of a chilled water system?
No, also on the closed
On the
loop.
closed loops,
Yep.
even for hydronic heatings?
Exactly. Remember, you have a closed loop that you have a pot feeder, right?
Yeah, pot feeder, yeah.
Okay, and you dose a lot of chemicals on that one. Every day or every week, you have to dose another one.
So it doesn't go through the same system, does it?
No.
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 You have to have
Separate.
separate systems
Yeah.
for the 3
Yeah.
loops,
The closed loop, you require a smaller unit.
smaller unit.
Yeah, because it's closed. You know, it goes back and forth
Yeah,
on
and
the same
you're
point.
less likely to get Legionella
Yeah,
there.
yeah. So yeah, we can do both.
Okay.
The closed loop, air handling unit. Okay.
And you're only choosing the solutions that you think will work on the system. You're not choosing all the solutions for every system.
What kind of?
So, for example, the ozone, the UV, the ionization. Do you use them for all system? You just you diagnose the system. And
Yeah,
based
depending
your
on what kind of bacteria we are looking. So if bacteria is Legionnaires or highly contagious bacteria, we have to use ozone.
But you wouldn't use that on a closed loop, right?
Yeah, we could.
You,
We could, yeah.
Could, you have to analyze what we have.
Yeah.
Yes.
We have to send that to a lab,
Yeah, oh, I see.
make it independent testing, and then the moment they give us the result, we'll apply the solution. We are actually custom built on what you have.
I see.
And if this chemical or this bacteria is consistent in your system, like every week you have it, every month you have it, we will apply the solution.
I see.
And the cheapest solution, cheapest and most economical. Because you generate it on site, you don't buy the chemical. You just keep on turning it on and it produces
The
the,
payback is about 3 years.
yes, less than 3 years.
Less than 3
Yeah.
years. Okay.
Yeah, with the auditor that they employed an auditor to audit what kind of savings we have on water, what kind of savings we have on chemicals, what kind of savings we have on labor. They said it's actually less than 3 years. Plus,
Our systems are small. Like, I mean, 4,500 GPM is about 1,800,
yeah,
1,900
19,
tons.
yeah,
We don't have any buildings that
yeah.
that big.
Anything smaller, like if you have a 300 tons,
300, 400 ton
Yeah.
would be the biggest.
that's a good one.
Yeah,
301 is very small.
yeah. Small
And,
unit.
yeah, small unit,
Small
we-
footprint.
Yeah, about 4 feet long, 2 feet wide by 5 feet high. And it weighs about 180 to 250 kilograms. And 2 or 3 people will push it with the wheel.
Get it through a door. And
Yeah,
just-
through the door,
it's
yeah, through the elevator and
Just
so on.
finding a room, because sometimes the rooms
Yeah.
in our mechanical
Yeah,
rooms aren't.
mechanical room, easily. In some occasion, because during winter, there's no flow on it. So it can go under the cooling tower on the roof. We can put it under the tower. Because during winter, there's no flow, there's no water on that. You have to drain it, or else all the pipes will burst. Yeah. Okay. These systems are the soapeners in the building. This is one of the high-rise building. Okay, next one.
Do you need softeners?
Yeah, we do softeners as well.
You
Yeah.
need them for the.
No, most of the time we tell them that you don't need the softener because you have a electronic precipitator. But some buildings, they still require, because the association know that the resin works for them. So I said, whatever works, I'll supply. But normally I don't, because it's a hard job to install a big tank, you know. Okay, here's the solution to HVACR. On disinfection methods, the scaling methods, disinfection, you have the ozone, which is this one. This is the smallest we have. It goes up to 5 grams or 500 gallons per minute, this unit. We go as high as 5 times of this, 5 times. We have that. And then we have the ultraviolet, especially on residential, small commercial. We do ultraviolet, UV light, copper silver for nasty bacteria you have, E. coli, Giardia on water, Listeria as well. And then you have a combined, we can combine the copper silver with precipitator, like this, we can combine. So you have the actual precipitation and then you have the killing of bacteria, okay? So this is before and after, actual picture, on a 1-inch copper pipe. After 3 weeks, we opened back again and we found that this is much cleaner and shinier. And this is about 1/2 the size from the beginning. So it closed from 1 inch, it becomes 1/4 inch opening. Okay. So this is the actual precipitator, the one that we have. Separator, system like this, and then multimedia. Again, the difference is that it can only go up to 5 microns of sediments removal. If you are sterile, like hospitals, you can go with multimedia, it can go down to 1 micron. Okay, but it's more expensive. But if you don't need to go 1 micron, this is the best because it is self-cleaning by itself. Okay? And then this is the manifolded sweeper nozzles in the basin. And this is one of the separator systems that we've shown, in a small 500 tons tower, cooling tower. And that's the patent, 105.26225. And so it's in the 1 million mark, so that means it was released only 3 years ago. After fighting the chemical company for 20 years, I got my patent. Okay, so this is how it looks. So you have the pump, okay, you have the strainer, you have the pump, you have the electronic precipitator, separator right here, and then your discharge filter is right here, and your purge filter is right here. So majority of the sediments will stay here, the carryover will stay here, collected, and then we inject the ozone right here. So when you have this in operation, you will see that by centrifugal motion, it creates a centrifuge, the solids goes down the bottom, the venturi actually goes back, the cleaner liquid goes back. Okay, thanks. Any questions so far? I need some question to go on. Yeah, go on.
You have not used this system for schools before, have you?
Pardon?
Have you used this system for schools before?
For school, I have, in California, I have about 11 of that. In Arizona, I have probably, based on my time with the company, I have 28 because of the hot weather condition in California and Arizona, and also the wind. If there's a lot of wind, it carries a lot of dust. So the windy area, I got most installation.
Got a lot of sand.
Yeah, sand is number one.
In the tower.
Yeah, towers, yeah. But in some areas, when there's a lot of insect, like the middle part, even here in Ontario, most need a centrifugal separator because the insect stays on the tower. So when they're heavy, because of the liquid that they absorb, they go down, and our sweeper nozzles will sweep it to the suction, the filter gets it. Remember, insects carry a lot of bacteria, especially when they are decaying. So you have to remove that in your tower basin. Only if you have tower basin. Some, they use air-cooled system. Okay. Okay.
How often do you need to clean this?
How often?
You need to clean because there are like sediments and all.
Normally, because you have a sweeper nozzles, you don't even have to clean it. The sweeper nozzle, the nozzle itself, do the job. They push. At the end of, say, the season, like you're going to close the tower because winter season, you need to clean it by using a certain chemical. So when you clean it, drain it, you have to use some chemicals to disinfect the system. Because when it's dry, we don't have the ozone. We cannot use ozone. So you have to disinfect before you drain the whole thing. Okay, remember the size is like this. For every system that you have, it will look like this. That's your sun filter or multimedia, but the tower system looks like this. You have the panel, you have the separator, you have the ozone, and you have the precipitator right here. Okay? You have the base, you have the suction, the pump, the suction strainer, and then you have the discharge filter. So whether it's small or big, it will be in the same category. Same. Okay? Okay? Oh, yes. Well, we'll be in touch, okay? Yeah, if you have problems, let us know, and then we'll come to help. Okay? Thank you for coming. Okay. Now, here is the program that we use. This is available to you, you know. So if you have a cycles of concentration of 3, which is normal, standard, in any use, 3, that means the cycles is probably between 600 on the system, recirculation system, 600 TDS, which is total dissolved solids, and your makeup is 200 parts per million. So you divide the recirculating flow rate or system by your makeup, you get 3. That's your cycles. And it determines how much water you're using with the cycles, okay? So the lower the cycles, the more water you use because you are bleeding or you're blowing down, okay? So this is the program. Current program is 3 cycles of concentration. The delta T, which is the temperature between the top and the bottom, is 10. And as I've said, 1,500 tons of refrigeration times 3, rule of thumb, is 4,500 gallons per minute. That is the amount of water you're using for the system. So your load is probably 2/3 a year, you know, wintertime you're shut down and so on. So this is the calculation. In Toronto, you are charged, I believe, $8 per cube or cubic meter of or water and so on, or 100 gallons per. So it has an amount. You have to input the amount, say it's $5. And the use here is that whatever water you use, you have to discharge the same water. So you are charged twice. The one you use, the one you discharge. So you have twice. So this is your gallons per year of evaporation based on the tower size of makeup and savings from sewer diversion if you are recycling that water, and the gallons bleed per year. Remember, you have to bleed to maintain your TDS. Okay. The next one is our proposed program. Minimum, very conservative on the next one, current, and then proposed. Proposed is 5. Only 2 cycles increase. But in reality, our system can go up to 10 and 15. We can go set up the total dissolved solid set point to 1,800 parts per million. You know why? Because the sediments or the calcium carbonate are suspended because of our electronic precipitator. So it tends to suspend, crystallize the solids, the scale, so our filter can remove it. So this is now the calculation, okay? So based on 5, we save on gallons of evaporation, gallons of makeup, and we save on potential savings for sewer diversion and gallons bleed per year. We save on that. So on the third one is our calculated savings, cost savings summary. So makeup water savings is 2,052 gallons, and then bleed savings the same, and then annual water cost savings 10,000, annual sewer cost savings another 10,000. So sewer diversion alone is 41. You were able to reuse that water. So your total water and sewer savings is 61,000 based on that size. So a 500 will be 1/3 of this, about 20,000 savings. Okay. Again, this one is a measure calculation on the condition of the tower or the system, if you are scaling or you're corroding. If you follow this formula, this program, you just enter your data based on collected data, it will spit out on the LSI, the Langley Saturation Index or Scaling Index. between -1 and +1, that range, you're actually good. Okay? So if you have a 0.15 positive, you are good. You are neither scaling or corroding. So there are two comments between 1936 and the last one is 1965. So these are two factors, Carrier and the other one was done by Lansley. So with this, you are assured that you are within that range. So our target is -1 to +1. This is the LSI. You calculate it, you use the program, it will give you whatever you are. And by that range, you can tell, oh, we are corroding, we're scaling. No, it's a very simple program, but it tells you your status, Okay, next one. So these are the references that I use based on that research. Any other question? Okay, my question is, if you have such problems, just give us all the data that you have, the water parameters, based on alkalinity, conductivity, TDS, and pH. Based on that, I can calculate the best solution for you.
Fortunately, the person that could give you that is not here today. So that's why Devin said, like, if you could send us some contact information,
Yeah.
we could do
We
a
will.
Teams meeting, maybe for even a new school. That could be something we look at. I don't know.
Yeah, for sure, we'll coordinate. We'll coordinate that one. Yeah. And the next one, probably in about a month or 2 months from now, and you will be invited. We have developed a magnetic power generator using permanent magnets and using batteries. You don't need solar, you don't need anything. Yeah, you enter your load, let's say you have a load of 100 kilowatts for one building and so on. We'll give you a generator, independent, off-grid or on-grid. You plug it on to your system, with an automatic transfer switch. You turn it on, all the loads in your building will be done by the generator. It could be a backup, because right now you have a backup diesel genset.
Right.
So you already have a permit for the diesel genset. It's a backup to your backup. Or it could be your duty unit. Or you can save a lot of power.
You can offset you can get off the grid.
You can get off the grid, and it will come. And we will invite you through William. We'll invite you to the next exhibit, which is the ADM in Metro Convention, Toronto.
Okay.
It's actually October 21 to 23.
Okay.
Yeah, I won't be there, but these guys will be there. I'm going to another exhibit in Manila. Yeah,
nice.
It's a big one. Yeah, big one. Yeah.
All right,
Okay.
well, thank you very much.
Thank you very much.
I'd like to get some of those
Yeah.
documents.
Yeah, and then we will send you this presentation as well, and some other presentation like the brochure for individual technology.
I can send you one presentation.
Yeah. Send all the presentation that we have.
If you want, just send it to Colleen.
Colin will distribute. Thank you so much.
Mag-wash pa ako.
Sige, balik ka. Usap pa tayo.
Trying to